Okay, thank you. So as I pointed out, when this is recorded and posted in your Blackboard, by mistake, it says lecture section 2, combined lab 51 and 52. This should be combined lab 53 and 54. Okay. So today it's only a lecture for you guys. So there's a 50-minute presentation that I'm going to do, and let me show you the problem that we're going to do. But before that, are there any questions? Are there any questions? So the problem that we're going to do is right there. It's coming from chapter 6 of your book, and it's a C clamp. It's a clamp like that. It's an object like this. And the inside of this hole is clamped, fixed, okay? And this face, this side is pushed down by some amount, 0.01 inch. What we like to know is, first of all, what is the stress distribution in the part, and how much force is needed to push this thing down by 0.01. Now I'm going to solve the problem two different ways. First one, just like it's done in the book, no planes of symmetry are taken. Then I'm going to come back and try to see if there are any planes of symmetry, okay? Because all your problems on the test is going to say use all applicable planes of symmetry. Okay, so let me ask you a question. You look at this problem, pretend that Z is going up, Y is going towards in the direction of the arm, and X is coming out like that. So X, Y, Z. Can you tell me how many planes of symmetry do you see? Z is up, Y is going like that, and X is coming out of the plane like so. How many planes of symmetry do you see?
2.
You see 2 planes of symmetry. Let me ask you this. For planes of symmetry, first of all, the thing must be symmetric with respect to that plane. I have a hole up there, I don't have a hole at the bottom. So strictly speaking, if Z is going up, Y is coming like that, and X is going like this, XY is not a plane of symmetry. YZ is a plane of symmetry, Z going up, Y going like that. YZ is a plane of symmetry, but not XY. So this problem has one plane of symmetry. And so when I run this problem and I do the problem second time, I use that plane of symmetry. Now, that the person who said 2, most people who said 2 are probably thinking about this problem. So first of all, the geometry must be symmetric with respect to that plane, and the loading is such that it must create a symmetric deformation. This is not the problem that I'm trying to model. It's a problem, but it's not the problem that we are trying to model. Okay? So this has, in the book, no planes of symmetry are used. I'll do that, and then I come back and do it with one plane of symmetry. Okay. That being the case, are there any questions? Okay. So that being the case, let me go and start a part file. I'll call this thing part. Immediately, I save it. File, save management, save as, desktop, new folder. This is lecture section 2, May 14, 1 week is gone. C clamp. Where was it? I did that right here. C clamp, clamp. Oh, okay. Clamp. Oops. It's called Clamo. That's fine. Okay, let's make it. On the vertical plane, I will sketch. Now we'll sketch something that looks like that C, and then we come and clean it up, like so, up, horizontal. Okay. Now I tried to make it so that this is kind of symmetric, but let's not worry about that. Make sure that this line control that line, control the middle axis. It's symmetric. It's shifted a little bit. No, my guess was wrong, right? Okay. Now notice that I can take this and move it around, and it will change exactly the way it's supposed to be. Everything is symmetric. Okay. All right, let's put some dimensions here. The dimensions, this radius is 1, I believe. The other radius is 2. Okay, and that length is, I believe it is 3. Check it out. Yep, but is it a 5 or a 3? Yes, 3. Now there's a circle there. Doesn't look right. Is this, what does it say? That says 3, right? Yeah, that says 3. Okay, so it's okay. Now, I'm going to draw a circle there. We move in, zoom in. Okay, and I want to make sure this circle is halfway between these two. So top line, control the bottom line, control the center of the circle. You make it see equidistant. And the radius of that circle is, I believe, the diameter is 0.5. And the position of this from that line is also 0.5. From here to there is 0.5. At the end of the day, you draw this any way you want, and that's fine. So then we're going to pad it in both directions, each direction being 0.5, which means a total thickness of 0.1. Okay? The reason I did it in both directions is that I want to cut it later on with this plane. Remember you said that this is a plane of symmetry? Yeah? Later, not now. So we apply material on it. It's made out of steel. Steel on that part. We say okay, and we save it. Okay. We're going to go to generative structure analysis. It automatically sees a 3D object. It's going to mesh it for us. Okay. With that size element, it's a static problem. And if you look at this, it's a parabolic element. That's fine. I have no problem with it. Okay. And the inside of this is clamped. Okay, it is clamped. You can see that. You can see inside of it. It's kind of hard to see what's going on there. And then we want to push this thing down by 0.01. That's by itself a vague statement. What do you mean push this thing down? How are you going to do that? Are you going to take somehow this corner point and attach a hook to it and then pull it down with a rope or something? Or are you going to take this edge somehow, take the whole edge down by 0.01? Are you going to the face? So this is ambiguous by its nature. We're not going to ordinarily, we're not going to let you, we're going to tell you what to do and then you do it. But if you're doing these things for real life, then you better know, what does that mean, pushing it down? How does it work? How is that thing pushed down in the real life by 0.01 inch? Okay. For this problem, I'm going to assume that entire face is pushed down. Every point on that face is pushed down by 0.01 inch. We don't know how to do it though, but we will. Okay, do you know how much force I need? The answer is hell no. In fact, one of the tasks that you have to do is to find out how much force is needed to do that. Now, there's one more thing I want to do is I want to take a final. Well, let me ask you this. Where would the critical area for this problem be? Over here. I hope that's what you meant by radius. Yes. That being the case, I want to make a finer mesh in this area. So you know how to do that because you're going to be asked to do it on the test. So in this tool, model manager toolbar, that there's a traffic light here. If you look at the second toolbar on the left, there is one of them which says local mesh size, and you select this, and notice that on this surface, it takes an element of that size. Okay, it knows it because I did it about 10 minutes ago or half an hour ago. I don't know, for the other lab. Okay, so if you're going to change this, you can do it here. But CATIA will remember these numbers that you input. It's unfortunate, but it does. Good. You want to see your mesh? Right click, mesh visualization. There we are. You see? That's killing a fly with a cannon. But anyway, that's what it is. Most of the elements are that size, but in this area that you insisted to have a finer mesh, is like this. Okay, good. Deactivate the mesh. Deactivate the mesh. Save the analysis. Do not forget to save the analysis. People, including myself, we leave this thing until the very end, and sometimes we forget and we panic, you know, etc. So file, save management, there is the analysis file, save as, in that same folder that I created for you, and I give it a descriptive name, no planes. Symmetry, I'll also say C-clamp, right? Because if you look at this, you don't know what the problem was. No planes of symmetry. We have done many of them. So there we are. Let me say OK. Now, how do we push this thing down? If you look at these icons, there is a clamp. No problem. We know what it means. Any point that you clamp does not move for this problem in the direction X, Y, Z. Any node or any point. Surface slider. Whenever you have symmetry roll, this is a roller. This one user defined a strain. We did problems together yesterday with the block. Wait a minute, you guys met me. I think we did this thing on during your lecture on Tuesday. Yeah, block with a hole. Do you remember that? Okay. The 1, 2, 3 rule. Remember that? Now there's some of the stuff here, but I can tell you that if your objective is to pass this course and hopefully do well in it respectably, this is all you need. Okay. Now, when it comes to load, there is pressure. So I put the pressure on a surface, into or out of. There's a force here. We did it several times. You put it on a point, on a face, on an edge. There's the acceleration. Remember the Newton's apple? Gravity. Okay. This, you don't know what it is. This last one looks like temperature. This second last one looks like temperature, and it is. This one says enforced displacement. It sounds like what I want. Enforced displacement of 0.01 inch downward or upward in some direction. The only problem is that when you click on it and you try to pick something, it won't pick it because it is expecting you to select a restraint. Now you can select this restraint, but that's not going to do me any good because that is a clamp that's fixed. Cancel that. So what we want to do is to want to have a restraint here. In applying non-zero displacement in CATIA, you have to do it at 2 steps. First, you make it 0, and then you can change it. Because when you make it 0, you create a restraint. And then you can select that restraint. So here is the user defined. This face, I want to make sure it is 0 downward. Because I want to change that, right? I want to create a 0 displacement on this face in the direction Z, because that's the only way I can change it. Okay? And now I click on that enforce displacement. And now I can go and select this guy, either from the tree or from the screen. See that? You can also select it from the tree. This is the one that I just created. See this? Or from the tree. And it says, okay, The amount is 0.01 and in the negative direction. How did it know it was 0.01? Because I worked with the other section an hour ago. I put a 0.01 here, it remembers, unfortunately. Good. Okay. Save the analysis before we run it. And I told you why it's a good habit to save before you run, because in the event that you accidentally put a tiny little element here and you did not pay attention to it, this may take an hour to run. By that time, the test is over and everything. So if you want to kill the job, make sure you have saved it up to that point. It's just that you go and change the size of the element. That's all. Now let's run it. Good. First, look at the deformation. If this looks weird, it means that you made a mistake. You have to go fix it. Yeah, that looks good. Looks good to me. See that? If you take that face and every point on it, you insist that it goes down by 0.01, this is the way it's going to look like. And do you want to know how much? By how much? So, well, you click on the displacement. It says by 0.0116 inches. Okay. Let's change the rendering here to average ISO and material shade. Average ISO is fine, except that look at the colors. The color is going to be in the line form. Okay, this is the old days when people had the inkjet printers and they wanted to make sure that they didn't pay for the ink. You know, they would draw it like this and others like that. So, but these days you don't have to do that. And if you want to look at the elements, rendering at the very bottom, question mark, there we are. Okay, good, good. 0.0116 inches. That's, what is that? 0.01 is about 0.2 millimeters, right? Something like this. Yeah. Now, what about the stress? Well, there we are. The stress is 9,400. Red spot is over there, just like you told me. Somebody said around the radius. I think that's what they meant. 9,400. So at least things qualitatively looks what I expect. Now I have a few questions for you. Is this a big stress or a small stress? This is steel, right? What do you say? There's a design engineer who's trying to design this thing. Would you say they'll have to worry about that stress or not? Because the biggest is this number. What do you say? Are you alive?
I would say it's decent.
Decent. Means it means it's low or it's
It's
okay.
it's kind of high, maybe.
Oh, okay, okay. Now, what is the yield strength for steel? Ballpark figure. In PSI, of course, in PSI. If you don't remember, go to your part. Did somebody answer what in the statement? Yeah, okay, don't worry about it. I'll take back what I said. Forget about this. Steel, 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 steel. I'm sorry, I didn't pay attention to this. Okay, so let me remind you, if the answer that this last person gave me is correct, but that's MPa, I asked for PSI. So I suggested to you is take the Young's modulus of steel in PSI, knock it down by 3 zeros. Or if you don't remember what the Young's modulus for steel is in PSI, just go to your part, double click on steel, select the tab which says analysis. It's got the numbers in it. It gives you the Young's modulus for steel in PSI. Actually, down here, it gives you a ballpark figure of the yield strength of steel, 36,000. See, if you knock this down by 3,000, by three zeros, you get roughly that number. So the stress that we got was 9,400. It's a third of that stuff. Okay, so whoever said that's decent, yeah, I like that because it's not high. This is why the displacement was, because the displacement was so small, 0.01. Okay, so let me look at the displacement. We already looked at, but there's something I want to show you. Average ISO, that's the one. So the biggest displacement is at in this area, the dark red area, and it's 0.0116. Wait a minute. I said 0.01. How did it become a 0.0016? Use your common sense. If I say displacement 0.01 in the z direction, well, I mean, common sense tells you that displacement should not be bigger than 0.01. Can you help me with this? If you know, that's okay. I don't expect you to know. Could this be wrong? Maybe I made a mistake somewhere. Okay, you see, translation. The displacement translation has three components. Translation in X, which I don't know what it is. I didn't say it. Translation in Y, I don't know what it is. I didn't say it. And translation in Z. That's the one that I imposed. In other words, what you see in the legend is a square root of displacement in X squared plus displacement in Y squared plus displacement in Z squared, which I said 0.01. So there's some other stuff that's going to get added to it, and there's going to be very small though, but that's why it's bigger. If you want to see only the downward displacement, so you double click on this, you say vector component, more, don't show me C1, show me C3. There we are. The biggest downward displacement is 0.01. This is the one that I imposed. There we are. Okay. So I hope that tells you there's a lot of this little thing. These are little important things that, yeah. One other thing before I go to the next other problem, notice that there is a box here. It says deformed or undeformed. If you uncheck the deform, it actually doesn't show you the deformed shape. Everything is going to be shown on the undeformed shape. Okay, so just letting you know what it is. Okay, good. Deactivate that. So we save this. Save it. We already did. Okay. Now we're going to repeat this problem using the plane of symmetry, which is YZ. YZ is a plane of symmetry. I'm going to kill this. I'll go to that. And I'm going to save it under the different name because I don't want to ruin this. This was good. File, save management. This guy, I'm going to save as this with one plane of symmetry. How about that? I should have called the original no planes of symmetry. I don't know. One plane of symmetry. Okay. Any changes that I make is not going to affect the original part. Now we're going to split this. Now, we already have a plane that I can use it for splitting purposes, YZ. But on purpose, I pretend that I don't have a plane and I need a plane halfway in the middle. So here's what you're going to do. You don't have to do that. You can use the YZ. You're going to say plane. The method of creating the plane is parallel through a point. It says parallel to what? Okay, parallel to YZ. Through what point? I want a point halfway exactly in the middle of this. So I say right click, create a point between this point and that point exactly in the middle, or you can say it a third of the way or fourth of the way. The ratio is 0.5 middle, right there. You say okay. Notice that as soon as I say okay, it creates a plane right there, even if I didn't have this guy down here to use. And I can use it for splitting purposes. The reason I did this thing on the first homework assignment that you're going to get, the plane, you have to make it yourself. I mean, unless you are very careful in how you make your model. There we are. Okay. Now, we're going to go to generative structure analysis, static. I don't like this rendering. Obviously, it's possible to change these things, but to go to the setting options, settings, and default setting. You can change these things. I don't like that grayish color. Grayish color is because you applied material. It shows you with the material on it. Now, the inside of this is clamped. Very good. And we know how to do it. We make it 0 displacement here, and then give it downward displacement. So 0 displacement in the direction Z, because now we can go and change it. We can go and change this. And we make negative 0.005, half. Anybody alive? You're going to lose 2 marks on this if you do it.
I think you would use the full value.
Yes, because it's displacement. Everything. Yeah, you're right. Good. Excellent. Can I run it? Can I run it? I don't want you to lose your 2 marks. Deflection looks okay, no problem. But look at the side view. What is missing? Now, I can change the scale here to make it more visible, probably. Let's make it 300. Let me zoom in. You see what the problem is? See that? Shrinks. What is the problem? There's something. You're going to miss 2 points. The question is, what did you not do that you deserve missing those 2 points?
Because you cut, so you have to set the side, the inside to with the I forgot the name. The reference
Surface
point?
slider.
Yeah.
Surface slider.
Yeah.
Roller, right? Surface slider. Because you cut it, you can't leave it alone. Symmetry means that it can't go sideways. So we say, okay. We run it. Say, okay. Don't worry about that message. This has to do with the surface slider. Now, if you look at the view from the front, or the side actually, and you look at the deflection, it doesn't matter how much you zoom in. The left side does not go to the left. You see, this one will shrink because it's a free surface. And before, since I didn't put any constraint on the other side, roller support or surface side, it also went sideways. But regardless of how much you zoom in within numerical error, that's good. Okay, 1 mark. Von Mises stress. Rendering, change the rendering. Material shading. Isn't that what I had before? Almost. Okay, I had before 9,330. Now it's 9,290. Okay, look, this is a numerical calculation. The difference of this and the previous one with the full model is about 0.3% or something like that. So obviously, they're not going to be identical. Okay, good. A couple of questions. Let me go ahead and change the element type. Oh, by the way, if you yeah, I didn't refine. I didn't refine here. Remember, I didn't refine. In the previous one, I did refine. This one doesn't even have refinement. Okay, that means that refinement was really not needed for this problem. If you're looking at here, because they didn't change that much. But I'm going to change this thing to linear and run it. There's going to be 10% difference. Linears are cheaper, but less accurate. But it may not be 10%, may not be important to you. It was 9,000, right? It's more. This one is actually more than 10%. It went from 9,300 to 7,000. So if you got this, and you were careless about doing a convergence study. You just made a run with linear element, look at the result, and you say, oh, the biggest stress is this. Well, that is bad because you're off about 15, 20% of what it should be. And that 15 and 20% could be getting it into a limit, the yield zone or not. The other thing is that with linear element, you can see that this patchiness, unless the mesh is very fine, this patchiness tells you that the mesh is not big enough. I mean, small enough. So let me go ahead there and change this thing to a smaller size. So for example, 0.1, how about that? 0.1, still linear, bad. But let's see what happens to the stress. Let's look at the stress. It was 7,200 something. Now it's 9,000. You see that the patchiness is kind of gone. And what we get, what we expected from parabolic one. Okay, now one thing I forgot to do. Now I'm going to do that right now. Okay, I'm going to do that right now with you. You know what? Let me save this thing. Let me save this thing. File, save, manager. I want to go to the previous model. Save as, desktop. This is one planar symmetry, right? One planar symmetry. One thing I forgot to do when I did it a few minutes. Cancel. File, save management, analysis, save as, one plane of symmetry. One plane of symmetry. Okay. And the reason I did this because I want to bring the other one and show you what we can do. File, see that over here? It says no planes of symmetry analysis right there. You see, it's so easy to figure out where they are now. This is the one that we did a few minutes ago. And if you look at the, look at the stress distribution, you can see exactly what it was. Okay. Now, suppose I wanted to know how much force is needed to push this thing down. You put the cursor on sensors, right click, create resultant sensor, reaction sensor. Click on it. It's expecting, you want to find the force somewhere. That somewhere can be where you said go down, or it can be that clamp, because the force downward is the same as the force for the clamp. Reaction force is up here. But let me do this. So I go to that restraint, downward displacement that I gave, right there. And I say update. It'll give you the amount of the force needed to push this thing down by 0.01 inch, which says it's negative 257 pounds. So you got, you're shown how to create sensor because we wanted to know what the force needed is. So let me save this. Now I'm going to kill this. I don't have to kill it. I can bring the other one. There it is. There's the other one. I want to find the force here. Okay, so put the cursor there. Let me deactivate this plot first. Right click, create resultant sensor, reaction sensor, select either the top or this guy meaning that restraint which allows you to push it down right there, and update, and it's minus 133. So what did I do wrong? The first one was 200 and something, I don't know, 60, 70. This one is 130.
Wouldn't it be twice that since it's half
Yes,
apart?
yes. Because the other 130 was on the right side of this that we didn't model. Okay, and in the old days when people were writing in-class tests and we would collect their papers and mark it based on that, on a problem like this, we would put a box there. And we'll ask the question, write the number that is the force necessary to create the following deformation. So what they have to do, if they did it like this, because they have to use plane symmetry, they have to rate 133 times 2, or negative 266, whatever. And there will be no room for argument. So you have to multiply this thing by 2 in this problem. And don't get the impression that every time you do a problem, you have to multiply something by 2. Use your common sense. Okay, so save this. Now you see why it's so important to give these meaningful names. I don't have to go to my folder. All the recent ones are saved here, and then you can get it from that place. The last problem that I want to do today is, okay, the last problem that I want to do today is this. What if I had a problem like that, and I wanted to do the same thing? Okay. So first of all, the geometry must be symmetric. If it's not symmetric, forget it. So you go to that sketch, you select the circle, and you mirror it with respect to the horizontal axis. We already used one plane of symmetry, cut this. Now we're going to use another one and use the XY plane. And it doesn't matter which side we pick, like this. Since I'm not going to save this thing, I will just go ahead and recklessly do this. Okay, so we go to generative structure analysis. I will regret it, but that's okay. Okay, clamp there. Surface slider at the bottom. Yeah. And if you want, you do it again, or you can put it both in the same place. Surface slider here. Okay. And you want to push this thing up by 0.01. So first you make it 0, because otherwise we can't enforce it. So on this face, in the 0 direction, don't let it bother you, because this has the direction of direction, but 0 is 0. There's no this direction doesn't mean anything. And now you can go change. Change it right there. This is the restraint. And it was not negative, because for this part, it's going to be plus, right? We're going to push it up. So 0.01. Good. I put all my surface sliders. I put the load. This is called a load, because when you're moving something by 0.01, you must have applied the load. That's why you see that displacement under the load icon, a toolbar. This will not run. And I want, cancel. This clamp should go. There's no clamp there. Let me show you what I said. This is the problem that we're doing. There's no clamp there. I mean, this is ridiculous. Why would you put a clamp and then try to do this? Okay. So let's run it. You will see that it will not run. And I want somebody to tell me, well, what went wrong? Any suggestions? CATIA sometimes can help you. Plot the deformation. It moves as a rigid body. It's like a fridge. Wheels at the bottom, wheels on the side against the wall. It can still move. So what we need to do, this is the 1, 2, 3 rule, but the 1, 2, 3 rule is not always 1, 2, 3 rule. You have to fix it. Basically, 1, 2, 3 rule is fixing it in a way that doesn't give you artificial stresses. So I'm going to say user defined. Remember, this was moving in the direction Y. I want to restrain that movement in the direction direction Y. It can't go up anyways, so because there's a surface slider here, and say, okay, this will not let it go sideways. Where is it? This is not the same problem that we solved the first 2 times. It's a different problem. You understand that? Didn't bomb out. I can't animate. That's because it used the scale to scale it down so that I could see before. Say default. There we are. and it deformed the way it's supposed to. If you had this thing and you pulled it from both sides by 0.01, this is what's supposed to happen. Now, this question came up with some of you guys. Let me deactivate this. Is can I use a clamp instead of doing this? The answer is if you're lucky and you select the right point, it doesn't matter. So let me delete this and put the clamp over here, because notice that there's a surface slider on that side. Essentially, that surface slider, the top and the bottom, says that it cannot move in the direction X or direction Z. And all I did was to add one direction 2 to it. So essentially, it's the 1, 2, 3 rule in disguise. This will work exactly the same way. But if you put it on the wrong place means on this side, that's going to be a different problem. This is exactly the same thing. Okay? But if I take this, deactivate that. If I take this clamp and instead of putting it there, I put it on this side, not two of them, I don't want this. Okay, if I put it on this side, the colors may look okay, the numbers will not be okay, and so if you use a clamp, if you're lucky, it may work, but use your engineering judgment. Why are you, what that clamp does? Okay, look, yeah, this one is wrong. In fact, if you look at it, where is this? If you look at it, you see, there seems to be something wrong here. Now, let's go ahead and dig in this thing a little bit further. Let me go here and make this thing parabolic. So this is linear, so let's look at it like that. And yeah, so let's run it. Show you in a minute. I want to use a better mesh, so that's what I need to change. Linear to parabolic. Activate this. You see, where is the biggest stress? On this side, right on this side, but it's supposed to be pretty much exactly the same. Now, to convince you, let me do the following, deactivate. Let me go ahead and make a box group over here. So, or sphere group, it doesn't matter. Sphere group. It's a huge sphere. So let me resize it. Okay, let me resize it further. I want to get very close to that edge and move this thing a little bit there. So it only shows me the stresses in that vicinity. This is not good. Move it a little bit like that. Say okay. Show me the stress. Double click on it. Show me the sphere group. What was that? Yeah. So you see, what I was trying to tell you is that that sphere group was not big enough. So let's go ahead and change it. Double click. Show it to me. Resize it. Where is that? Must be another handle or somewhere. Remove this thing. Oh, there. Okay. So activate. Hide. See, the biggest stress is because you're fixing this point. This face is supposed to be able to shrink, but when you fix this point, means that there was surface slider here on this side, and you won't let it go sideways. So there's going to be a big stress here. There's going to be a stress here